Welcome to our lecture 5. Today we're going to introduce and cover linear combinations, and then later on we're going to start talking about linear transformations. So first comes first, we first have to tell you what is an n-tuple of vectors. So let us start with V, a vector space over R, and n a natural number. Then an n-tuple of vectors is just an element of the Cartesian product of V to the n. So you can think of it as just an enumeration of n many vectors here. So keep in mind that this has nothing to do with R to the n, unless V is really the vector space R, but also it doesn't have anything to do with really the vector space R to the n in that case, because here there's no structure, there's no adding or something or scalar multiplication on this tuple V1 through Vn. So the point is really just here, we want to be able to kind of enumerate and keep track of this data of n different vectors in V. And so for some convenience, a zero tuple will just denotes the empty tuple, and we'll use this we use this notation throughout the class. And so now doing this, we can define what is a linear combination. So given an n-tuple of vectors from a vector space, we say that a certain vector in V is a linear combination of other vectors, so of an n-tuple of vectors, if they exist scalars such that this vector can be written as, well, a linear combination of the others. So meaning there are scalars lambda 1, lambda 2 through lambda n, such that V is equal to lambda 1 V1 plus lambda 2 V2, and so on until plus lambda n Vn. And just to give it a name, these lambdas are called coefficients of the linear combination. And as a convention, we let 0 be the only linear combination of the empty tuple. So if you want to look at, let's say, the set of all linear combinations of a certain tuple, then the one of the empty tuple will just be 0. So let's look at some examples. So first, well, let us place us into R to the 3, and let's look at the vector 2, 1, 2, 3. This is a linear combination of, let's say, 1, 0, 3, and 0, let's just put pi in the middle, 0. Well, y as 1, 2, 3 can be written as 1, 0, 3 plus 2 over pi. Yeah, this is a nice real number, like this. And see how here I already blurred kind of the distinction between row and column vectors. Yeah, in fact, we would want to write here one, 2, 3 is equal to 1, 0, 3 plus 2 over pi, 0, pi, 0. So the reason is that in general, I want to stick to writing all elements of R to the 3 as row vectors. And then later on, when we're going to talk about bases, I'm going to write coordinate vectors. So if you don't know what they are, we will introduce them later on. So so-called coordinate vectors will be written in column vectors. And so since the distinction is already kind of difficult to cope with in general, I really want to make it visually distinct if I'm talking about actual elements of R3 or this other type of vectors. But that will follow later on, just as a heads up. Now, secondly, let's look at something that is not a linear combination. So let us place in the same vector space, and let's look, for example, at the vector 0, 0, 1. This is not a linear combination of the tuple 1, 1, 0, comma 0, 1, 1. And so why is this? As the equation lambda 1 times 1, 1, 0 plus lambda 2 times 0, 1, 1 equals to 0, 0, 1 has no solution. So you can able to check that in more detail. But if you want to do that, right, you would start that lambda 1 here has to be equal to 0 because you want that lambda 1 times 1 plus, well, nothing here is equal to 0. So lambda 1 has to be equal to 0. And then, well, then you have that lambda 2 times 1 is equal to 0. So lambda 2 has to be equal to 0. Great. So now let's come to our first theorem here. So the theorem states that if I take a vector space V and then I take a subspace of that vector space, and in that subspace I'm going to take an n-tuple from vectors in W, then any linear combination, this tuple, will again be an element of W. So we want to prove this. So consider a linear combination lambda 1 W1 plus all the way up to lambda n Wn. And so as always, I just want to keep track of what are the inputs. It's a linear combination in this tuple, and I want to really tell the reader, well, these lambdas will be real numbers. And so now I kind of go at this step by step. The first thing I'm going to argue is that these elements here, lambda times the wi's, will be in the vector space. So first, note that lambda I times wi is in W for I from 1 through n, as W is a subspace of V. Yeah, one of the properties of a subspace is that it's closed under scalar multiplication. And so since these wi's were already element of W, then lambda I, the scalar times the wi, will also be in W. And so now we have these elements in W, and we want to argue that their sum has to be. And we kind of have to go this inductively, about this inductively. Now, since W is closed under addition, we can conclude lambda 1 W1 plus lambda 2 W2 is also an element of W. And then now repeating this argument, we can get that the whole sum will be in W. So now the whole linear combination will be an element of W. And this is what we wanted to prove. Observe we could have proven this by induction, or we could have kind of actually be doing this, we're proving this by induction, but what I mean is like we could have also written it down as an induction. And so we will learn this later in more detail, how to prove by induction if you haven't already learned this before. Okay. So now we go to our next theorem. So the next theorem states that if you take a family of subspaces, and maybe I'm going to say a little bit more to this, what does this mean? Okay. Here an example for such a family is the following. We could have I equals n, and then we have that I in I, right? In this case would be I in n. So this would be the same as, well, having W1, W2, W3, and so on. For each natural number, we get one subspace. This is one example of such a family. We could also have that I is just a finite set. Let's say it's 1, 2, 4, 16. Well, then I in I, what do I get? Well, I get the W1, W2, W4, W16. And so when it's finite, we can just really enumerate this. We can write it as the other thing. If it's the natural numbers, as in example 1, we can give it somewhat an enumeration. But what you could also have is like I equals R, and then I in I is really just, well, I in R. And so now there's really no easier way to write this down. So this just means for give me any real number and I associate a vector space to it. So this is the first notation here that is important. Then what is the second notation? Is this intersection. So what is the intersection of I and N, Wi, this big intersection? This should be the intersection of all of them. W1, W2, W3, and so on. So this will be an infinite intersection. And the second one, if I is this 1, 2, 4, 16, then this big intersection with I and I, Wi in this case, will be, well, W1, intersection with W2, intersection with W4, intersection with W16. Sorry for this pause. I, for some reason, lost track of my notes here, so I'm right where I want to be again. Okay, sorry for this. And then in number 3, what do I have here? Well, then there's really no easier way of writing this, yeah? So this will be just the intersection of all of these. Okay. So I hope this will give you a good idea of what this family means, and also what this intersection means. You're more than welcome to ask me about this in the live lecture, and I'd be more than happy to elaborate more on this. But let's go back to what the theorem says. The theorem says now if you've given a vector space and you take such a family of Wi of subspaces, then the whole intersection will be a subspace again. And this is one of your homeworks for next week, to show this. And I would recommend here to use the subspace test. Great, so this is all I wanted to say about subspaces, about linear combination and subspaces there. Now let's go ahead and talk about linear transformation. Let's start out with the definition of a linear transformation. So first of all, you can think of a linear transformation as a function. So it's a function from one vector space to another. And we say it's a linear transformation if these two properties hold. The first one is that it commutes with addition. So basically it says that whenever I add up things in the vector space on the left and then apply the transformation. I could also apply the transformation first and then add up. And the second says it commutes with scalar multiplication. So it says that, well, it's the same, first multiplying an element times a scalar and then applying the map, which is the left-hand side, or I first apply the map to a vector and then I multiply times the scalar. And we also just often call this that T is a linear map. And so now first, this is kind of the fundamental properties of a linear transformation that we want to prove now. And so what you should think of a linear transformation is basically a function between two vector spaces that preserves the entire structure. And as for the axioms, we want to kind of keep the definition as small as possible, as slim as possible. So we don't want to really add extra information. So since we want to preserve the structure, one of the things we would want is that the neutral elements get sent to the neutral elements. And so this is part one here. And also we would like that the additive inverse gets sent to the additive inverse, if that makes sense here. But we don't have to add it into the definition because there already are consequences out of the definition we've given. So these are the first two which we want to prove. And then the last one here is another characterization. So it's one of these if and only if statements. I'll say something again about how to prove them, but let me first say about what this means here. If you have such a statement where you have a property on the left and something else on the right, it's basically an equivalent definition for this property here being linear. And what it says now here is that you can put 1 and 2 into 1, meaning, well, it's enough to check that this linear combination is equal to this linear combination on the right. So this basically takes care of addition and addition and scalar multiplication at the same time. So let's go into the proof. So number one, we want to show that T of 0 is equal to 0. And we're going to use a cancellation law. So let us start out by T0 plus T0. So the idea is to modify this to get something of T0 plus 0 in the end. So what we do here is in every time we modify this, we're going to give a reason why. So over each equal sign or beside it, wherever how you want to indicate it, you really want to let the reader know what is your argument to do this modification. So in this case, we want to use property 1 of being linear. So meaning that you can also first add 0 plus 0 and then apply the transformation, or first apply the transformation and add up. And then we have to go into the vector spaces. So axiom 3 here means, well, 0 plus 0 is just equal to 0 because adding 0 to anything doesn't change anything. Then we're going to apply axiom 3 again, but outside. And also note here now what is happening is inside here V and V, so all of these are zeros in V, same here, but this here is now the 0 of W. So it's actually potentially a different element if V doesn't coincide with W. And then we can use axiom 1 to swap them around. And then by cancellation law, we have what we want. And so again here also, if you're going to go back into the statement, this is the left-hand side 0 is V and the right-hand side is W as well. Okay, that was part number 1. Now part number 2 is left as a homework problem for next week. So just to let you tell you again, what should the idea be here for this guy? Well, you want to show that the left-hand side is equal to what? The unique additive inverse of t of v0. So this is how your proof should go. Similarly as the properties of the axioms, the properties of the vector space, you want to show that the left-hand side has the same property as the right, meaning show that t of v plus t of minus v is equal to 0. This is the clue here. Great. And now let's go to part number 3. Part number 3 tells you, well, you want to show that it's linear if and only if the other thing. So first reflex you want to have here, if and only if, tells you that you have to prove both directions. So let's start with this direction, meaning we're assuming it's linear, and we want to show that the right-hand side holds. So now let lambda be in R and v1, v2 be in V. What can we do now? Well, then let's compute this. So t of lambda v1 plus v2. What can we do? And so basically we're going to go back to the definition of being linear up here, and we first going to use part 1. So we can pull it apart at the plus sign. And then we're going to use t is linear, part 2. Well, we can then pull this apart, meaning we'll pull apart. We can pull the lambda out. And this is precisely what we wanted. Okay, this was the easy direction. And if you can actually spot which one is the kind of easier direction, I would always recommend to start with that one. First of all, it prevents you from forgetting that one after done the more complicated one. And secondly, it gives you a good feeling, yeah? It seems like you already have half the work done, which is not necessarily true, but you know, in a midterm, sometimes it's also about like having confidence of being able to do it, or even in a homework. And so already being able to do one part probably motivates you of being able to do the second part. Okay, so now conversely, suppose that t of lambda v1 plus v2 is equal to t of lambda v1 plus t of v2 for all lambda in R and v1, v2 in V. Great. So now we want to show that it's linear. So showing that it's linear, we have to show both points. First the addition and then the scalar multiplication. But before we can do that, we have to kind of redo part 1 here. So first note that t of 0 is equal to 0 under this assumption. Right? Now the only thing we know is that t satisfies this, but we're not assuming it's linear, so we don't know 0 gets it to 0. And this goes very similar to the one before, just with a little more subtleties. Let's start with this, okay? And what we kind of have to do is here, we have to add ones into the picture. What's the reason? Well, the problem is that this part here, right, does not tell you that now you can put the 0 together, yeah? You really always have this lambda here around, yeah? And so the lambda will be here 1. So then by the assumption, we can now pull this in. Now, let's use axiom 5 and axiom 3 at the same time. Axiom 5 tells you that 1 times 0 is 0, and axiom 3 tells you that if you add 0, this doesn't change anything. Now we're doing axiom 3 again outside for W. And then we do axiom 1 to turn them around, to switch them around. And then by cancellation law, we can conclude. And so now we can finish taking lambda equal to 1 proves the first part of linearity. So here we really didn't need anything else. And taking V2 to equal 0 proves the second part of linearity. And so here we needed that T of 0 is equal to 0. Why? Because, well, let's go back. What does that mean here? If we take 0 equal to 0 up here, then we get that T of lambda times V1 plus 0 is lambda times T of V1 plus T of 0, but this is 0, and then we get that this is lambda T of V1. Okay, and so this finishes this proof over here. And now we're going to finish the class by some examples. Suppose we have some m and n in the natural numbers, and we take a matrix that is an m times n matrix. Then the following map is a linear map, and so we denote this map by T of A. And note, we're going to do this throughout the entire class. So this is an important example of a linear transformation. And what are we going to do is, well, T of A of some vector x is going to be equal to A times x. Yeah, note here x is an n-dimensional vector, yeah, in R to the n. And this follows from the facts of vector multiplication, and we'll use this throughout the class. Attention, notation used throughout the class. So in the future, I will not really give the definition anymore. Sometimes I might to recall, but the more I do, the less I will do it later on. So T subset of a matrix will always correspond to this type of map. And so note again here, we kind of blur the line between row and column vectors, because again here this has to be a column vector for this to make sense. But as I said, we usually stick to thinking of Rn as a row vector, but for some things we might have to go from one to the other. So this is number 1. Let's do number 2. Suppose X is a non-empty set. Now recall if I take the set of real value function on X, this is a vector space over R. And let us take an arbitrary element in X and see, this is why it has to be non-empty, because we want to take one. Then EV index X0, which goes from F, which is this vector space, into R, is going to send a function to its evaluation at x0. So this EV x0 denotes evaluation at x0. And this is linear. Again, check at home. And last but not least, let's look at the following ones. And this again will be notations you should be aware of and will be used later on. Let's take two vector spaces over R. One important map is the following. 1v, v to v. So this, you have to have the same vector space. And you're just going to send every element to itself. And this is called the identity map. It is linear. And actually, it's a bijection. Secondly, we also have this map, the zero map from V to W. Okay, so the first one will indicate the domain, the second will indicate the codomain. And what it does, it's just going to send everything to zero. The zero map. And this is also linear. Great, so this will be all for today, and I hope to see you all on Friday. Bye-bye.